Hello all, welcome to this video where we look at exponential models and their applications. So this is effectively what we've been building towards this whole topic, this whole chapter is we're not just doing maths for the sake of maths, we're doing maths so that we can apply and use it, be useful, solve day-to-day problems. We have here 4 different exponential models or rules or equations that come up in common problems. They're the most common locations that we see in exponential growth or decay. One is cell growth. So we have n equals n naught 2 to the power of t on td. One thing to note with this td is that's generation time, which is effectively the time for a cell to divide. Okay, that's what TD is, the generation time. We have radioactive decay, so any radioactive element, atom, will decay after some time into some other element or atom, sometimes into another radioactive element, sometimes into a non-radioactive stable element. But this talks about A is equal to A naught e to the power of negative kt. So if we have some amount or mass of a substance, so we might have 500 grams or 1 kilo of uranium or plutonium, or there are very common ones that we deal with, but there's a whole bunch. It works for anything. It's dependent upon, commonly when we think of radioactive decay, we talk in times of half-life, which is how long it takes for half of the current substance to decay. Half-life is a separate number to this k. This is also called the decay constant. This is really useful because we can use it in this equation. Our half-life value or half-life time, we need to do stuff to it to turn it into k to be able to use it in this equation. So that's why we're dealing with this decay constant. And it's just it's technically a percentage time, but like we can just think of it as it's dependent on each different type of element. We then have population growth and population decline. We've seen both of these in year 10 maths, and they're actually these equations are being used a lot all around the world at the moment with the COVID-19 situation. I remember with my year 9 class, before we went into isolation, we were using these to predict what are going to be the numbers in Australia or worldwide after 30 days, after 60 days, after 90 days. And we remembered we were predicting when it was just first kicking off, we did 90 days and it's going to be 1.1 million. And everyone in the class was like, oh no, it's surely not going to happen. And you look where we are now, and that was infections. And now we're dealing with there's over 110,000 deaths just in the United States of America alone. So that shows that scary idea of exponential growth. It grows and it grows on top of its growing, and it grows quickly. It grows exponentially. It's quite a scary thing in the wrong situations. One thing to point out with the population growth and decline equations is that this whatever our rate is, the time unit for our rate, for this rate needs to be this. We then need to use the same rate here, okay, or time unit. So if we're given our rate in percent per year, like a interest rate per annum, well then that means we need to deal with years. N needs to be in years. If it might be a growth rate of cells per day, or not even cells, it might be who knows what it is, but an exponential growth or decay that's might be 3% per day. Well, that means we're now dealing with our N needs to be in terms of days. So you need to match your N, or convert your N to match the unit in the rate. So that's really important. You can pause the video here to copy these down. I highly suggest you have these copied down. You're going to need these. You're going to know what each of the variables within them mean. Couple key things that I want to point out is notice that our time variable is in the exponent. Okay, so that's why we're normally dealing with that's sort of what we're used to calling our x. Yeah, we're just in most of these it's time instead, and it's in the exponent, so hence we're dealing with an exponential equation. The other thing that might be new to you is E, this E here. Okay, E is normally called Euler's number. Now Euler is actually spelled sort of, some people call it Euler, but Euler's number, and that is, it's like pi, it's an actual, just it's a number, it's 2.718 keeps going on. Okay, and it's an irrational number, just like pi. Okay, but that's what it's equal to. For now, we're going to just leave it at that. It's just, that's that number, and it's used a lot in a lot of different growth and decay and exponential models. But for now, we'll use it. To be clear, actually, I'll talk about it later, how we do a log of base E. But there are 4 equations. So let's have a go at them. Okay, a population of 2,000 pathogen cells doubles in time every 15 minutes. So for our equation, we're dealing with n and n naught. So this is our n naught, and this is our TD. And it's asking for us to determine a formula for time in t minutes. And that's really nice because it matches that. So we get n is equal to 2,000 times by 2 to the power of t on 15. And there's our equation for this given situation. How long will it take for the population to reach 12,000? So that is our final amount. Give your answer correct to the nearest minute. So we're trying to find n. Actually, we're given n, we're trying to find the time. So we get 12,000 is equal to 2,000 times by 2 to the t on 15. We can divide 2,000 by both sides, so we end up getting 6 equals 2 to the t on 15. Using our log to convert this, we can now say that that is equivalent to log of base 2 of 6 is equal to t on 15. So we then get 15 log base 2 of 6 is equal to t. So therefore t is equal to, and this is where in all these application ones you're going to be using your calculator. It's not something that you're going to know off the top of your head. You can make an estimate. So log base 2 of 6, that's 2 to the power of what is equal to 6. That's going to be 2.5-ish, a bit more. 2.5 times 15, we're going to be in the 38 range. So let's have a go at that, if I can get my calculator to turn on. Okay, so 15 log base 2. Sorry, the calculator's, the battery's dying on, it's giving me grief. It's alright, we'll go to the internet. 15 times log of base 2 of 6. That is 38.77. I was pretty darn close with my estimate. I like that. Okay, so we get 38.77443. Keeps going on and on. So t is roughly equal to 39 minutes. So it only go from 2,000 up to 12,000. So it's 6 times larger. But because it's doubling every 15 minutes, it doubles on top of the double. So after the first 15, so we got 0. Let's do a little table. Okay, n at 0, we've got 2,000. After 15 minutes, we got 4,000. After 30 minutes, we've got 6,000. After double, sorry, that's 8,000, and then after 45 minutes we're going to have 16,000. So that's doubling on doubling on doubling. So it only took 39 minutes to get up to 12,000, which was 6 times more than the original amount. Right, okay. After 3,000 years, a sample of magnesium-23 is decayed to 40% of its original mass. Determine the formula for the radioactive decay of magnesium-23, where K is a positive constant and T is time in years. Okay, so we're dealing with time in years, something to note. After 3,000 years, so that's handy, it's the same unit, decayed to 40% of its original mass. Okay. So let's think of this 40% of its original mass. What is that saying? Well, that is saying, if we use the same A and A naught, we have some A naught original amount and some final A amount. That A is equal to 40% of A naught, or our original moment, or A is equal to 0.4 A naught. So we get that, and we can use that, sub that into our equation. So we've got 0.4 A naught is equal to the original amount, e to the negative kt. E to the negative k, and t in this case happens to be 3,000 years. If we want the more basic version of that, okay, we just have A is equal to A naught e to the negative kt. That's the base version where we're starting to evaluate stuff, or substitute in, I should say. Find the value of K, correct to 7 decimal places, and hence find the half-life of magnesium-23. So there's 2 parts to this. We first need to find K, and then how can we use K to find the half-life? Because that's generally what we want to know about certain radioactive materials, is we want to know the half-life, because once we know the half-life, we can then make predictions and use the amount of elements in items to carbon date them. That's effectively what they're doing, is looking at the carbon decay of an item, how much carbon's left in it. So let's have a go. We've got this 0.4 A naught is equal to A naught e to the negative 3,000 K. We can divide both sides by A naught, so that cancels off. So we get, wrong color, 0.4 is equal to e to the negative 3,000 K. Using our log to exponential equivalence and conversion, we could say that that is log base e to 0.4 is equal to negative 3,000 K, and we get K is equal to log to the base e 0.4 on negative 3,000. So what's K going to be equal to? Now, this is harder. Like, how do we do log to the base e on your calculator? Now, most calculators will actually have a button for this. They will look like, though, okay, and just on our calculator right over here, the top left, log to the base e is written on your calculator as ln, and that's short for log natural. Okay. Log natural, because the other thing, that e, Euler's number, is also called the natural number, okay, and that's terribly written, log natural. Okay. So that will be on your calculator. It's generally right near your log key button. Looks like ln. Okay, so I have this on mine. My calculator's working now, so we get log natural of 0.4 divided by negative 3,000, and I get 0.0003054. So that's 7 decimal places. That's what I needed. 1, 2, 3, 4, 5, 6, 7. Yes, 7 decimal places. So that's the first part of it done. We've found the value of K. Correct terminal. Hence, find the half-life of magnesium 23. Okay, so what do we have now? Well, we now have, if we think of our general form, we've got A is equal to A naught E to the negative 0.000305 T. That's a general equation for magnesium 23. We found our K, which is our decay constant. How can we use our decay constant to find our half-life? Well, after one half-life, our remaining amount of material is equal to half the original amount. Okay, that's after one half-life. Okay, so we can substitute that in and cancel out our A naughts, and we're going to end up with just T left. So let's put that in. So we get half A naught is equal to A naught E to the power of K value, 3054 T. Again, cancels out. So we are left with half is equal to E 03. Why did I make this to 7 decimal places? Okay, so we get log to the base E of half is equal to negative 0.0003054 T. So T is equal to log E to the half on negative 0.000354, and that is equal to log natural of 0.5 divided by negative 0.000354 enter is equal to 2269.637. So it is roughly equal to 2270 years is the half-life of magnesium 23. That is a long time. If you need more time to copy that down, you can pause the video as always, but I'm going to go on with the next example. Okay. And this time it's a population growth. Hopefully you're feeling this one will be a little bit more familiar, because these are the sort of ones we did in year 10 mathematics a bit more. Okay. But in a large country town, the population P0 of rabbits at the start of 2003 was 3,500. By the end of 2013, this number had increased to 27,000. Assumed growth is exponential. Determine the formula for the population growth of the rabbits, where R is the rate as a percentage and N is the number of years since the start of 2013. Okay, so N is the number of years since the start of 2013. So what are a couple of things that we have? Well, P0 is equal to 3500. The final amount in 2013 had increased to 27,000. Okay, and N, the number of years elapsed, okay, isn't 2013. It's how many years since 2003, so N in this case is going to be equal to 10. So we can say our equation, the base form, to remind you, is P0, 1 plus R, and this is an exponential growth, so we got a plus, R on 100 to the N. Okay, so there's our base equation, so we could write that as 27,000 is equal to 3,500, 1 plus R on 100 to the 10. Okay. Find the value of R, and hence find the predicted population of the rabbits at the end of 2020. So we need to find the rate of growth as a percentage, and this will be a per year percentage because that's what our time unit is in. Right, so we're pretty much going to solve. We just need to solve this equation. The only thing unknown in it is our R. Okay, so let's start rearranging that. So we get 27,000 on 3,500 is equal to 1 plus R on 100 to the power of 10. Okay. Now, this, where is our unknown? It isn't in the exponent anymore. We have 10 in the exponent, so we don't actually need to use a log to solve this. Okay, we have to the power of 10. So since we have the power of 10, well, to undo the power of undo, okay, or to change the equivalence, okay, we take the 10th root of both sides. And that'll equal to 1 plus r on 100. So what do we get from here? Take 1 from both sides, so we get the 10th root of 27,000, 3,500 minus 1 equals r on 100. So we get 100 by the 10th root, and I can cancel this down. I can take some zeros out, so we get 270 on 35 minus 1 is equal to r, and we can just stick this in our calculator to find out what r is. 100 times by the root of 270 divided by 35. We'll take away 1, close brackets. Oh, that's what I did the square root. I need to do the 10th root. Okay, 10th root of 300 of 270 divided by 35. There we go. Okay. Yeah, when I just did the square root, I got a rate of 177%, which is insane. No, the rate of population growth is 22.6675. Keeps going on and on. Percent. Okay. So we now have our rate of growth. We can now use it to find the population of the rabbits in 2020. So we want to find P, where P0, we're still starting with 3,500. 1 plus, we now have our rate, 22.6675 on 100, all to the power of, and again, we're not going to put 2020 in as our power, okay? It hasn't been 2,020 years since our population started. Okay, population started in 2003, so it has been 17 years. Again, stick that into your calculator and you'll get your answer. Divided by 100 to the power of 17, we get 112,841.74. Okay, which is roughly equal to 112. I left a 1 out. Okay, 841, and I haven't rounded up because you can't have half a rabbit. Okay, or 0.74 of a rabbit. According to this, after 17 years, we're going to have 112,841 rabbits, approximately. Okay. So that's that problem. Again, pause now if you need more time with it, but I'm going on to the next problem. This one, and this is more from a textbook, it's just good to be able to do though, is if we're given just some coordinate points. So this is taking a step back. It's not so much applied. This would be a step if you're an interpreting problem. So you're given a couple data points. So it could be, say, after 1 year, the population of rabbits was 6. After 5 years, the population was 96 if you're given it in that form. Or you could think of it in terms of X and Y. And you know that the growth is going to be given by some exponential equation. How do we find that? What is that actual exponential equation? And so this is effectively simultaneous equations. So if we substitute in, let's call this coordinate 1, and then we substitute these data points in again to our unknown exponential, we get these two equations. A times b to the 1 is equal to 6, and a times b to the 5 is equal to 96. And this is most easy to solve by doing 1 divided by 2. So just to show you the actual working out, that turns into a times b to the 1 on a, actually we're going to do 2 divided by 1. That's a much better way to do it, avoids negative powers. 2 divided by 1, we get a times b to the 5 equals 96 divided by a times b to the 1 on 6. So a's cancel, and we're left with b to the 4 is equal to 16. Okay, so we could say b to the 4 is equal to 2 to the 4, therefore b is equal to 2. You could also, if it wasn't so nice numbers, you could solve that b to the 4 equals 16. If that wasn't nice, you could just solve it using a log now. Here's another example for you to have a go at. Exact same process as this slide. Exactly the same process. I'm not going to actually go through it, but you can have a crack at it. And then the very last slide, so pause now if you want to have a go. And then the very last slide is that we can do this on our CAS as well. We can still solve just like any other form of simultaneous equation or system of equation as it's called on the CAS. You need to make sure you define it, okay, with your two unknowns, and then you use your menu algebra, solve system of equations, choose two equations, and then input it like that. How do we get this and in? Actually, before that, don't forget, if you want to put restrictions, okay, and I should actually go back to point out this restriction. In this case, technically this could be plus or minus 2, okay, but since we're told in this problem that b needed to be greater than 0, okay, that means b will be positive 2 and not just and not plus or minus 2. And then the last bit, to find a, you would substitute back into one of these equations to find out what a is. But yeah, if you're given those conditions, okay, remember this is called the pipe. It's called pipe. Okay, it's the technical name for that symbol. It means given on the CAS, and you can bring that up on your CAS. It's in the same button as the greater than, less than menu. So bring it up that, and then how to get this and is you literally type it. As you first start typing, you type in your A and then your N. It'll be italicized, but then you put your D in and the whole word will change into actually saying and. So to get that and is you literally just type it in. And yeah, you can solve simultaneous equations that are exponentials. CAS will do it fine. That's it for 13H. Have a crack. Most of these examples are very similar to the ones in the textbook. So when you get the textbook, okay, recognize, is it a cell growth? Is it radioactive decay? Is it a population growth or decline? With the radioactive decay, this idea here that a half-life is when the final amount is equal to half the initial amount, being able to use that and substituting it in, okay, here, substituting in, that allows you to find out the actual time period elapsed of the half-life. That's a common gotcha. But apart from that, that's it. Hope this helps. If you have any questions, like always, ask in class, ask on Compass, ask via email, or ask in the Edmodo class. Thank you very much and have a good evening.